Welcome to Journey Through Time, where we travel across centuries, lands, and ideas, slowly unfolding the great questions that bind us to this planet. Whether you're listening under a blanket, sitting on a balcony at sunrise, or closing your eyes after a long day, this story is for you. Together we'll explore Earth, its fragile balance, its hidden forces, and the unfolding changes that test the limits of habitability. Earth feels steady, the same blue sky, the same moonlight, the same seasonal rhythms. We build homes, raise families, plan futures, and quietly assume the planet will stay our home. Yet sometimes, late at night, a question arrives. Could that ever change? Could Earth become uninhabitable? It's not fire and brimstone or explosions. It's subtler. Systems shifting just enough to unravel food, air, and shelter. Humans, with all our tools and machines, might one day look back at Earth from somewhere else. For most of its 4.5 billion-year history, Earth has been hostile to life like ours. Primitive microbes floated in nutrient seas, or clung to deep-sea vents long before oxygen filled the sky. Humans need a tight set of conditions: temperature ranges, atmospheric pressure, fertile land, stable seasons, fresh water, and a protective ozone layer. Even in our brief window of stability, Earth has swung through ice ages, warm periods, and extinctions. Entire ecosystems vanished when change outran adaptation. Today, the unusual part is not that the climate is shifting, but how fast, largely because of us. Asking if Earth might lose habitability is asking whether we'll push it too far, whether our burning, building, and extracting will nudge the planet's systems past their limits. The very intelligence that built cities and decoded biology could also test Earth's resilience. To understand the risk, we start with what makes Earth habitable now: the Goldilocks zone. Not too close to the sun to boil oceans, not too far to freeze them. Earth's orbit is nearly circular, keeping seasons moderate. Our atmosphere, 78% nitrogen, 21% oxygen, with slivers of CO2 and other gases, creates the pressure and mix we need. This delicate balance formed over billions of years, as photosynthetic life reshaped a toxic sky into breathable air. Gravity holds that air. The magnetic field shields us from cosmic rays and solar winds, preventing our atmosphere from being stripped away like Mars's. Water exists abundantly in all three states: solid, liquid, gas, enabling glaciers, rainfall, and weather cycles. Biodiversity stabilizes everything else: trees absorbing CO2, bacteria fixing nitrogen, insects pollinating crops, coral reefs buffering coasts. Together, these systems act like a biological insurance policy, but each is vulnerable. Lose enough species, and the system falters. Melt too much ice and sea levels rise. Dry out aquifers and deserts expand. Pollute rivers or deforest tropics and feedback loops accelerate. Habitability rarely disappears overnight. It frays, region by region, as heat, drought, storms, or rising water overwhelm human infrastructure. Earth will persist as a rock in space, but its capacity to support our societies is what's at stake. Scientists describe 9 planetary boundaries: climate change, biodiversity loss, ocean acidification, land system change, and more. Thresholds beyond which Earth may shift into unstable states. We've already crossed several, or stand close. Instability doesn't mean immediate collapse. Some tipping points are reversible. But the question isn't only whether Earth can remain habitable, it's whether we'll keep it that way. Even small margins matter. Move Earth a few million kilometers inward, and oceans boil. Tilt the axis too much, and seasons become catastrophic. Lose the moon's stabilizing pull, and our axial tilt would wobble, disrupting climate. The quiet details, orbital shape, atmospheric chemistry, rotation speed, are why we're here. They produce forests in some regions, deserts in others, predictable planting and harvest, and stable coasts where civilizations rise. Yet every one of these quiet systems can be stressed. Magnetic fields weaken, biodiversity erodes, water cycles misalign, carbon levels climb. The balance that feels eternal is in fact a narrow zone. Understanding that zone, its geology, biology, and physics, is the first step toward protecting it. This is where our journey begins, not in disaster, but in recognition. Earth is strong yet sensitive, ancient yet changing, a well-tuned instrument carrying the weight of life across millennia. By seeing its margins clearly, we glimpse both the fragility and the possibility. If you've ever watched a sunrise wash gold across a landscape or stood under a soft evening breeze, you've felt Earth's balance, not inevitable, but earned through countless interacting systems. The Sun, our star, is unremarkable by galactic standards, but steady enough to anchor life. Earth's nearly circular orbit keeps temperature swings modest. Our 23.5° tilt gives us seasons without extremes. The Moon stabilizes that tilt and shapes tides, which once may have nurtured the molecules of life. The atmosphere acts as a transparent shield, filtering sunlight, trapping warmth, and burning up small asteroids. Oxygen, the most visible element for us, took billions of years to accumulate. Too little and complex life never emerges. Too much and fire risk skyrockets. Carbon dioxide, often vilified, is also essential. Without it, Earth would freeze. With too much, it overheats. The narrow band we've had during human history made agriculture and cities possible. Water cycles knit everything together. Evaporation, condensation, and precipitation drive weather and nourish land. Yet water is unevenly distributed. Some regions rely on monsoons or melting snow, others on aquifers thousands of years old. Infrastructure stores, diverts, and rations water, but prolonged drought or failing systems can tip regions from livable to precarious. Even fertile soil is not guaranteed. It's alive, microbes, fungi, minerals, a quiet engine of food, water retention, and carbon storage. Degrade it, and the foundation weakens. Plate tectonics slowly recycle carbon and regulate temperature. Without them, atmospheres can vanish or freeze, as on Mars. Earth's 24-hour rotation creates day-night rhythms, shaping migration, sleep, and countless biological clocks. Slow the spin too much, and one hemisphere bakes while the other freezes. Speed it up and storms rage. Our ordinary rotation is another hidden blessing. All these variables line up just right to make Earth not only habitable, but livable, rich, and varied. Air supports life, life supports soil, soil supports water, water shapes weather, weather cycles nutrients. It's not a machine, but a self-adjusting network honed over eons. Humans have been here only 300,000 years, a blink. Civilizations with writing and cities cover barely 5,000 years. We arrived during an unusually calm period, the Holocene, which gave stable temperatures, rainfall, and sea levels. In that window, we built agriculture, culture, and science. That stability built expectations: breathable air, drinkable water, tolerable temperatures, winter following fall, sunrise after night. We plan months ahead, build permanent structures, and invest in futures trusting the environment's basic rules will hold. But when they don't, wildfires, floods, crop failures, we're reminded how dependent we are on systems beyond our control. Earth's habitability isn't a permanent feature, but a fragile agreement between biology, chemistry, and physics. Right now, that agreement is under strain. The atmosphere, our thin skin of gas, is warming. Carbon levels are rising. Human activity drives it. Without a change in course, the systems that made this planet feel like home could falter. Yet even now, the air remains soft, breathable, full of wind, birdsong, and curling clouds. It's not lost, but it is changing. We live inside the troposphere, just 12 kilometers thick, where weather forms. Above it lie layers we rarely notice: the ozone-shielded stratosphere, the mesosphere where meteors burn, and the thermosphere brushing space. Our climate depends on that lower, dense pocket of nitrogen, oxygen, argon, CO2, and trace gases. Cyanobacteria filled it with oxygen billions of years ago, making complex life possible. This oxygen balance is maintained by the partnership between plants and animals. We exhale CO2, plants inhale it, and return oxygen. Tip the balance and the air starts to change. Fossil fuels inject carbon faster than ecosystems can absorb. Forests cleared for agriculture lose their carbon storage capacity and release stored CO2. Peatlands and wetlands disturbed by drainage or fire release centuries of accumulated carbon. Oceans absorb a quarter of our emissions, but acidify in the process, harming coral, shellfish, and marine food webs. Warmer water holds less oxygen, creating dead zones where life struggles. Greenhouse gases work as a blanket. Without them, Earth would freeze. With too much, it overheats. For 800,000 years, CO2 never rose above 300 ppm. Since the Industrial Revolution, it surged past 420 and climbing. Methane, from livestock, rice paddies, and fossil extraction, traps over 25 times more heat than CO2 over a century. Nitrous oxide, from fertilizers, is long-lived and potent. These gases aren't unnatural. It's the speed and scale that break the system. The feedbacks amplify each other. Ice melts, exposing darker surfaces that absorb more heat. Permafrost thaws, releasing methane. Warmer air holds more moisture, fueling stronger storms. One change sparks another and another, making it harder to stop the longer it continues. Yet ecosystems are resilient if given space. Forests regrow, soils recover, oceans rebound, up to a point. Beyond certain thresholds, recovery slows or halts. Climate change is often called a slow-moving crisis, but geologically it's happening at breakneck speed. Atmospheric CO2 hasn't risen this fast in millions of years. Species are going extinct at rates unseen since the last mass extinction. Earth can adapt, but not always at our pace. When adaptation lags, systems fail. Still, the atmosphere is one of the best-studied systems we have. We've measured it with balloons, satellites, and ground stations. We've modeled its behavior. We know what drives the warming and what slows it. Reforestation, clean energy, carbon capture. None are magic bullets, but all can help. The same feedback loops that amplify damage can amplify recovery. This isn't only about numbers, but about lived experience. The air we breathe, the water we drink, the seasons we trust. Every inhale draws in the remnants of leaves, oceans, and microbes. Every exhale feeds the cycle. Recognizing that cycle, and our part in it, is the beginning of repair. What we call weather is really the atmosphere in motion. Heat from the sun unevenly warming Earth, driving winds, clouds, and rain. The equator receives more sunlight than the poles, creating pressure differences that move air and water around the planet. Earth's rotation adds spin, shaping trade winds and ocean currents. Mountains, forests, deserts, and coastlines all contribute to this dance, turning sunlight into storms and breezes. Behind the daily chaos, there's usually an order: seasons, climate zones, predictable extremes. Climate is the average of weather over time. When we talk about climate change, we're talking about long-term shifts in patterns. Warmer winters, earlier springs, longer droughts, stronger storms. These changes ripple into everyday life through the weather we notice, and increasingly the weather is turning fierce. Heat is one of the most visible symptoms. Recent decades have seen record-breaking temperatures worldwide. Deadly heat waves stretch for days or weeks. In places where air conditioning is scarce or power grids are weak, extreme heat becomes a major health threat. Elderly people, outdoor workers, children, and those with existing conditions are especially vulnerable. Crops wither, roads buckle, and infrastructure strains. Wildfires grow more intense as vegetation dries, lightning ignites, and firestorms create their own winds. Storms, too, are supercharged. A warmer atmosphere holds more moisture, intensifying rainfall. Hurricanes and typhoons feed off warm ocean water and become stronger, forming faster, lasting longer, and dropping more rain. Storm surges climb higher, floodplains stretch farther. Flooding can come from heavy rainfall, melting snow, or rising seas. Even areas once thought safe now see streets underwater. Insurance systems strain, recovery costs soar, and rebuilding gets harder each time. Meanwhile, other regions face the opposite problem: drought. Shifting weather patterns leave soils dry and rivers low, agriculture suffering, reservoirs dropping, and wildfire risk climbing. Some droughts creep in gradually, recognized only in hindsight. Others arrive suddenly, forcing rationing, water restrictions, and migration. Even subtle misalignments matter. Spring arrives earlier, snow melts sooner, insects emerge before the birds that feed on them. Crops bloom out of sync with pollinators. Over time, these small shifts accumulate and ecosystems lose rhythm. Jet streams, those fast-moving rivers of air high above, weaken as Arctic warming reduces the temperature contrast with the equator. A weaker jet stream wobbles, causing weather systems to linger, extended heat waves, prolonged rain, repeated cold spells. Old records no longer hold. A 1-in-1,000-year flood may now happen every few decades. Rare heat waves become routine. Infrastructure built for a bygone climate falters under new extremes. Storm drains overflow. Power grids sag under demand. Buildings overheat. Emergency services stretch thin. Adaptation becomes less about preparation and more about catching up. Climate change amplifies existing weather, not creating storms from nothing, but intensifying those already forming. A heat wave becomes deadly. A storm becomes a disaster. A dry season turns into a drought. This amplification effect is consistent across climate research. The physics are clear. The outcomes vary by location, making adaptation tricky. What works in one place may fail in another. The consequences aren't only physical, but psychological. Disasters disrupt communities, displace families, and create long-term stress. Survivors of wildfires or floods often struggle with anxiety, depression, or grief. Rebuilding isn't just bricks and roads, it's trust, memory, and safety. As the sky grows more volatile, scientists ask how much warming humans can withstand before regions become difficult or impossible to live in. The concept of wet bulb temperature, combining heat and humidity, sets a hard limit. At about 35 degrees Celsius wet bulb, even healthy people in shade with water can die after prolonged exposure. Parts of South Asia and the Middle East are already approaching these limits during heat waves. These are not future projections. They're measurable shifts happening now. Efforts to slow these changes, emissions reductions, renewable energy, better forecasting, are underway, but weather moves on its own schedule. Still, data and models help. Cities redesign streets to manage heat, forests are managed to reduce fire risk, and floodplains restored to absorb water. These adaptations don't stop warming, but buy time and protect lives. Weather has always shaped human stories. Where we settle, what we grow, how we build. Now, as the sky grows louder and less predictable, it demands more of us. Not just to endure, but to understand and act. The carbon we emit, the land we use, the choices we make feed back into the sky. The storms, the heat, the rain, all connected to us. From here, the path leads deeper into the systems we depend on, into oceans rising and warming, currents carrying life, and the slow but steady march of sea toward land. Like a kettle coming to boil, climate pressure builds quietly, then crosses thresholds we can't ignore. These signals, flooded streets, failed harvests, days too hot to work outside, are warnings from a system under strain. Carbon dioxide isn't the only greenhouse gas, but it's the most discussed for a reason. It's the most abundant among those humans add, and it lingers in the atmosphere for centuries. Every ton emitted now shapes the climate decades ahead. Burning fossil fuels, coal, oil, natural gas, releases carbon locked underground for millions of years. When the Industrial Revolution began, atmospheric CO2 started climbing at a rate unmatched in geologic history. In 1958, scientist Charles David Keeling began measuring CO2 at Mauna Loa Observatory in Hawaii. His data, the Keeling curve, showed levels rising year after year, with seasonal fluctuations from plants absorbing and releasing carbon. The trend was unmistakable. For most of human history, CO2 hovered around 280 parts per million. By the early 2000s, it had passed 370. Today, it's above 420 and still climbing. The last time levels were this high, sea levels were meters higher, and global temperatures several degrees warmer, long before humans existed. Methane, over 80 times more potent than CO2 at trapping heat over 20 years, leaks from natural gas, livestock, rice fields, landfills, and thawing permafrost. Its concentrations have more than doubled since pre-industrial times. Nitrous oxide from fertilizer and industry is nearly 300 times as warming as CO2 over a century. Each gas adds to radiative forcing, the imbalance between incoming solar energy and outgoing heat. Greenhouse gases trap more of that energy, warming the planet. This is not theory. It's measurable by satellites and weather stations worldwide. Climate scientists use the concept of a carbon budget. How much CO2 can still be emitted before crossing critical temperature thresholds? The most cited are 1.5 degrees C and 2 degrees C, above pre-industrial levels. These aren't random. They mark points beyond which the risk of irreversible climate impacts rises sharply. Extreme heat, sea level rise, ecological collapse. Humanity has already burned through most of the budget for 1.5 degrees. What remains is small and shrinking. Every year of high emissions makes the remaining space smaller. Impacts grow quickly with each fraction of a degree. More coral reefs lost, more deadly heat days, more displacement from low-lying areas. And emissions are uneven. Energy production from fossil fuels is the largest source, followed by transportation, industry, agriculture, and buildings. Within these sectors lie solutions: cleaner fuels, better efficiency, less waste, smarter design. But implementation takes time, money, and political will. Carbon removal, pulling CO2 back out of the air, is gaining attention. Reforestation is the oldest approach. Trees store carbon as they grow. Other methods include soil carbon sequestration via regenerative farming, direct air capture with machines, and bioenergy with carbon capture. These are promising but not silver bullets. Most are costly or hard to scale. And scientists agree. Removing carbon isn't a substitute for reducing emissions. It's not enough to mop up the floor while the tap runs. Some emissions are difficult to avoid. Steel and cement produce CO2 as part of their chemistry. Aviation and shipping are hard to electrify. Agriculture emits methane and nitrous oxide from livestock and fertilizers. Yet innovation is happening. Alternative fuels, lab-grown meat, regenerative farming. But timing is critical. Gases already in the air will warm the planet for decades. The sooner emissions fall, the better the odds of staying within safe limits. Fairness matters. Nations that emitted the most historically are not the ones suffering worst effects. Island states, low-income regions, and vulnerable communities often face the brunt with the least capacity to adapt. Wealthier countries have stronger infrastructure and resources. International negotiations under the UN climate framework attempt to address these disparities, encouraging finance and technology transfer. Progress is slow, but signs of change are real. Record renewable energy investment, cheaper solar and wind, electric vehicles gaining share, cities updating building codes, businesses setting targets. The carbon clock isn't a countdown to doom. It's a tool showing how much time remains to change course. The choices made in the next few years will shape the planet, inherited by future generations. That weight can feel heavy, but it also brings clarity and shared purpose. The atmosphere responds to action. The same loops that accelerate damage can amplify recovery if forests regrow, if emissions fall, if systems shift. Look at the oceans, vast, deep, and quietly absorbing over 90% of the excess heat trapped by greenhouse gases. Without them, the air would be far hotter and climate far more volatile. But this buffering service has costs. Warm water expands, raising sea levels. Melting ice adds more. Coastlines creep inland. Saltwater intrudes on freshwater supplies, and high tides reach farther each year. Some changes measure in centimeters, others in how many times people rebuild. Currents like the Gulf Stream carry warm water from the tropics north, keeping Europe milder than its latitude suggests. In the southern hemisphere, the Antarctic circumpolar current loops around the globe, regulating heat and carbon flow. These conveyor-like systems depend on temperature and salinity differences. Fresh water from melting Greenland ice reduces salinity and weakens the sinking motion, driving the North Atlantic circulation. Disruption here could alter rainfall, weather, and sea levels across continents. The last time this system weakened sharply was at the end of the last ice age, triggering abrupt climate shifts. Phytoplankton near the ocean surface absorb CO2 during photosynthesis. When they die, some carbon sinks to the deep ocean for centuries, but warmer, more acidic water hampers this process. Ocean acidification, CO2 dissolving into seawater to form carbonic acid, lowers pH and makes it harder for corals, shellfish, and plankton to build skeletons. As foundational species decline, entire food webs shift. Coral reefs, the rainforests of the sea, provide food, shelter, and storm protection. When water overheats, corals expel the algae living inside them, losing color and energy. Repeated or prolonged stress can push reefs beyond recovery. Mass bleaching events have become more common, transforming vibrant ecosystems into pale skeletons. Recovery is possible, but not guaranteed. Deeper waters face oxygen loss. As surface layers warm, they form a barrier that slows mixing, leaving deep regions starved of oxygen. Combined with nutrient runoff from agriculture fueling algae blooms, this creates dead zones where few organisms survive. These processes interact, warming, acidification, deoxygenation, producing complex cascading effects on marine life and coastal economies. More than 3 billion people rely on fish for protein. Coastal economies depend on tourism, fisheries, and ports. As oceans change, Fish migrate to cooler waters, catches decline, coral loss reduces tourism, and ports must adapt to higher seas and stronger storms. Yet solutions exist: marine protected areas, sustainable fishing, restored wetlands, and ecosystem-based climate strategies like mangrove and seagrass restoration. These habitats store carbon and buffer coasts. Restoration takes time, but offers dual benefits: climate and biodiversity. Sea level rise will persist, even if emissions stopped tomorrow, because of thermal expansion and ongoing ice melt. This is not a reason for despair, but a reminder of urgency. Every tenth of a degree matters. Every year of delay adds to the challenge. The ocean touches everything, shaping weather, regulating temperature, absorbing carbon, sustaining life. And now it's moving faster, in directions that ask more of us. From the coasts, the story moves inland, to forests, soils, and fields, the living foundation beneath our feet. Soil is not inert dirt, but a dynamic system of minerals, organic matter, water, air, fungi, bacteria, and countless organisms. A handful can hold more microbes than there are people on Earth. Healthy soil anchors plants, filters water, stores carbon, and supports nearly every terrestrial food web. When it's healthy, it works quietly. When it breaks down, the consequences ripple outward. Agriculture depends on soil that can hold moisture, drain well, resist erosion, and support plant roots. Intensive tillage, monoculture planting, synthetic fertilizers, and pesticides degrade its structure and microbial life. Over time, this leads to compaction, nutrient loss, and vulnerability to drought and flood. Soil degradation also accelerates climate change. When organic matter is lost, carbon once locked in the ground enters the atmosphere. That warming feeds back into more droughts and extreme weather, further stressing the soil, a slow but heavy cycle. Regenerative practices, no-till farming, cover crops, composting, crop rotation, can rebuild organic matter and microbial diversity. These approaches aim not just to minimize harm, but to improve the land, making it more productive and resilient. Some farmers already see better yields, drought resistance, and lower input costs. Scaling this takes support, incentives, and time, but the potential is large. Forests cover about 30% of Earth's land area and act as carbon sinks, water regulators, and biodiversity havens. Trees absorb CO2 during photosynthesis, store it in wood and soil, and release oxygen. A mature forest is more than its trees. Roots, fungi, animals, and microbes form an interconnected system. Tropical forests, the Amazon, Congo Basin, Southeast Asia, hold massive amounts of carbon and moisture, influence global rainfall, and host much of the planet's biodiversity. Yet they are under pressure from logging, agriculture, mining, and infrastructure. Deforestation releases stored carbon, turning forests from sinks into sources. In the Amazon, researchers see signs of a tipping point where rainfall declines and some areas dry out, burn more often, and regenerate less. A shift to savanna-like ecosystems would reduce carbon storage and biodiversity, with global consequences. Boreal forests across Canada, Scandinavia, and Russia store vast amounts of carbon, especially in soils. But they too face rising wildfires, insect outbreaks, and warming. Fires in boreal regions release both tree carbon and deep soil carbon like peat, which burns slowly and is hard to extinguish. Tree planting is often promoted as a solution, and in some contexts it helps. But monocultures, non-native species, or planting in ecosystems not historically forested can harm biodiversity and alter water cycles. Reforestation works best when restoring native species, supporting local ecosystems, and integrating with other land uses. Pressure on land comes from agriculture and livestock, which use about 80% of farmland for meat and dairy, though those provide less than 20% of global calories. Reducing food waste, improving yields, and shifting diets even slightly can relieve pressure on forests. Land tenure also matters. Indigenous communities manage or protect a significant portion of the world's remaining forests and biodiversity hotspots. Where indigenous land rights are recognized, deforestation rates are lower and ecosystems healthier. Yet these communities often face political and economic pressures, undermining their stewardship. Beyond forests, grasslands, wetlands, and savannas also store carbon, cycle water, and support life. Wetlands are carbon powerhouses and natural water filters, but have been drained or degraded in many regions. Restoring them protects coasts, stores carbon, and buffers floods. Land is not a passive backdrop, but an active player in climate. It absorbs, releases, adapts, and transforms on human scales, seasons, meters, giving us a chance to influence it directly. Technology and policy can help, from satellite monitoring of deforestation to subsidies for sustainable farming. But much of the work is local and practical: planting, tending, protecting. As climate change intensifies, some land will become less productive under droughts, heat waves, floods, and shifting pests. But land can also be a solution, storing more carbon, producing food efficiently, and restoring damaged ecosystems. The knowledge to do this isn't new. It often draws on traditional methods and local observation. The seeds of change are in the soil itself, in forests still standing, and in decisions quietly made across fields and hills. Species loss ties into these changes. Extinction is natural over long timescales, but mass extinction compresses time. Earth has seen 5 major mass extinctions in the last half-billion years. Many scientists warn we're entering a 6th, not from asteroids or volcanoes, but from human activity. Habitat destruction, pollution, overexploitation, invasive species, and climate change all drive rapid loss. Species are disappearing at rates 100 to 1,000 times normal. Amphibians are especially sensitive to environmental shifts. Insects, often overlooked, show widespread declines in abundance and diversity. Birds tied to specific migration routes struggle to adapt. Coral reefs bleach and die. Large animals face poaching, slow reproduction, and shrinking habitats. But extinction isn't only about individual species. It's about the networks they form. Plants feed insects. Insects pollinate crops. Birds control pests. Predators balance prey. Biodiversity provides resilience. Lose enough species and ecosystems become brittle, collapsing under stress. This isn't just ecological, but practical. Our food systems rely on pollinators, our medicines on natural compounds, our economies on stable ecosystems. The loss of species diminishes not only nature, but our understanding of it. Some scientists caution we haven't yet crossed the threshold of a true mass extinction. Others say we're in its early phase. Either way, the trend is clear. Habitats shrink, pressures mount, and the background hum of extinction grows louder. Conservation works. Protected areas stabilize populations. Corridors help species migrate. Captive breeding rescues animals from the brink. International agreements regulate trade in endangered species. Indigenous groups and local communities often lead in stewardship. New technologies discover species faster and track them more precisely. Efforts are shifting from single-species protection to whole ecosystem restoration. These projects are complex, but offer hope. Not just slowing loss, but rebuilding abundance. The 6th mass extinction, if it continues, won't be a single moment, but a gradual erosion across lifetimes. That also means there's time, not unlimited, but enough, to change course, to value biodiversity as the living foundation of systems that sustain us. Whether a world emptier of forests and quieter in birdsong can still be called habitable is a question tied to our own survival. Technology now shapes the planet as much as nature once did. For most of human history, survival meant adapting to weather, seasons, predators, and soil. But with tools and machines, we began reshaping the world around us: dams, power plants, roads, satellites. And now much of modern life depends on hidden infrastructures, operating quietly in the background. Every leap in technology carried a footprint. Energy systems fueled by coal, oil, and gas powered the Industrial Revolution and still provide about 80% of global energy. These fossil fuels are dense and reliable, but release vast amounts of CO2. Extraction, refining, transport, and combustion all emit greenhouse gases. Transportation alone, cars, trucks, ships, planes, accounts for a major share. Electric vehicles are growing, but aviation and shipping remain hard to electrify at scale. Supply chains built on fossil energy reach into every product and service. Industry contributes differently, but powerfully. Cement production releases CO2 as a chemical byproduct when limestone becomes lime. Steel production needs extremely high heat, often from coal. These materials form the backbone of modern infrastructure: bridges, buildings, and ports, and alternatives, while emerging, are still expensive or in early development. Technology transformed agriculture too. Tractors, irrigation, synthetic fertilizers, and pesticides boosted yields, but also increased emissions and degraded soil. Fertilizer use releases nitrous oxide, a potent greenhouse gas. Clearing land for farming, especially in the tropics, drives deforestation. At the same time, cooling systems, refrigeration, air conditioning, data centers consume energy and often use refrigerants with high global warming potential. As climates warm, cooling shifts from optional to essential, further stressing power grids. Digital life brings its own environmental cost. Smartphones, laptops, and routers require rare earth metals mined through energy-intensive processes with social and ecological impacts. Cloud computing and server farms consume vast electricity. As digital infrastructure expands, so does its footprint. E-waste, plastics, and chemical runoff add persistent physical byproducts to the environment. Yet technology also offers tools to address these challenges. Renewable energy, wind, solar, hydro, is expanding faster and cheaper than once thought possible. Battery storage improves. Smart grids balance supply and demand. Electric vehicles grow more efficient. Charging networks expand. Energy efficiency, better insulation, lighting, industrial processes, saves money and emissions. Cities use data to manage traffic, reduce waste, and improve public transit. Carbon capture technologies remove CO2 from air or power plant exhaust. Some use chemical scrubbing, others enhanced mineral weathering or bio-based approaches. They're costly and not yet widespread, but could help sectors that are hard to decarbonize. Satellites monitor deforestation, ice melt, and sea level rise. Sensors measure air and water quality. Machine learning analyzes trends and improves forecasts. Early warning systems for storms and precision agriculture for water and fertilizer reduce damage and waste. Construction materials are evolving. Low-carbon cement, engineered timber, recycled steel, and 3D printing may cut waste. Retrofitting existing buildings often costs less and avoids emissions embedded in new construction. But technology alone can't solve the problem. Many emissions stem from how often we drive, what we consume, and how much we waste. Behavior and systems matter alongside machines. Trade-offs exist. Mining lithium, cobalt, and other battery metals can damage ecosystems and create new dependencies. Solar panels and wind turbines require land, raw materials, and end-of-life disposal. Building clean energy infrastructure fast enough for climate goals demands coordination, investment, and careful planning. Wealthy countries can deploy new technologies faster, while poorer regions, often facing the worst climate impacts, may lack resources to transition. Bridging this gap is part of climate justice. Technology mirrors human priorities. Used without care, it multiplies problems. Aligned with nature, it can become part of the repair. Efficiency, circular design, renewable power, and closed-loop systems are reshaping how we think about progress. Even with all our machines, we're not the only force acting on Earth. Some threats arrive from beyond: asteroids, solar storms, cosmic events. Roughly 66 million years ago, a large asteroid struck what is now the Yucatan Peninsula, triggering fires, tsunamis, and an atmospheric blackout that ended the age of dinosaurs. Today, thousands of asteroids are tracked. Most orbit safely in the asteroid belt, but some cross Earth's path. The annual risk of a large impact is low, but not zero. Smaller asteroids can devastate a city. The 2013 Chelyabinsk meteor exploded with hundreds of kilotons of energy. Detection and deflection missions like NASA's DART show it might be possible to alter an asteroid's path with enough warning. The sun itself poses hazards. It emits a stream of charged particles, the solar wind, and occasionally bursts with solar flares or coronal mass ejections. Large storms can disrupt satellites, radio, navigation, and power grids. The 1859 Carrington event lit auroras in the Caribbean and shocked telegraph lines. A similar storm today could cripple internet infrastructure and power systems across continents. Forecasting space weather is improving, but major storms remain hard to predict. Hardening infrastructure against such events is ongoing, but uneven. Beyond asteroids and solar storms lie rarer cosmic events: gamma-ray bursts, nearby supernovae, shifts in cosmic rays. Probabilities are low, but they remind us Earth's stability isn't entirely self-contained. Even space debris, fragments of satellites and rockets, threatens the satellites we depend on for monitoring climate and communicating warnings. Some see hope in space, exploration, expansion, or even escape: lunar bases, Mars missions, asteroid mining. But no place beyond Earth yet offers full conditions for long-term survival. Off-planet life would depend on artificial habitats, with perfect engineering and constant supply lines, far less forgiving than Earth's systems. Space exploration teaches us about other planets, and by contrast, how rare our own is. Satellites track weather, deforestation, ice loss, and pollution. Telescopes probe deep space and time, revealing cosmic processes that echo our own climate mechanisms. Recognizing these larger contexts reframes the question. Earth's habitability is not a given, but an active balance between internal systems, human actions, and cosmic chance. Seeing it clearly underscores both its fragility and our role in sustaining it. Earth exists inside a larger system, but our immediate challenge is still here at home: sustaining a planet that can sustain us. The changes underway are not isolated. They link atmosphere, ocean, land, and life in feedback loops. The more we understand those loops, the better chance we have to steer them toward recovery rather than collapse. Inside the oceans, forests, and soils, countless interactions store carbon, regulate temperature, and recycle nutrients. Microbes in soil fix nitrogen. Plankton in oceans draw down carbon. Trees buffer storms, and wetlands filter water. These processes evolved over millions of years. They respond to change, but only within limits. Push them too far, and the services we take for granted falter. In practice, this means agriculture, cities, energy systems, and transportation must all shift. Cleaner energy cuts emissions. Smarter land use stores carbon. Regenerative farming improves soil. Protecting biodiversity preserves resilience. Each measure adds up, not as a single solution, but as part of a whole. This is where policy, technology, and personal choice intersect. International agreements set targets. Governments incentivize renewables. Businesses redesign supply chains. Communities restore wetlands, plant trees, and build seawalls. Individuals conserve energy, reduce waste, and vote for policies aligned with sustainability. Small actions scale when multiplied. Some regions are already experimenting with adaptation. Coastal cities building surge barriers, farmers changing crops, architects designing buildings for passive cooling, and utilities investing in microgrids. These measures buy time and protect lives, but must accelerate to match the pace of change. The story of climate change is also a story of inequity. Those least responsible often bear the greatest burden. Island nations face rising seas. Drought-stricken regions lose crops and water security. Migrants flee areas no longer viable, sometimes encountering borders or hostility. Climate justice is not a side issue, but central to any realistic solution. Fair transitions, ensuring clean energy, resilient infrastructure, and conservation are accessible to all, matter as much as technological innovation. Indigenous knowledge, long marginalized, offers valuable insight into managing land, water, and ecosystems sustainably. Including these voices strengthens adaptation and stewardship. Beyond adaptation and mitigation lies restoration, actively rebuilding what's been lost, reintroducing species, replanting forests, reflooding wetlands, reconnecting rivers to floodplains. These efforts aren't nostalgia, but pragmatic steps to recover functions that stabilize climate and biodiversity. Each restored hectare, each protected corridor, increases resilience. Understanding that resilience reframes despair into agency. Climate systems are not static, but responsive. The same physics that amplify harm can amplify healing. Lower emissions mean less warming. More forests mean more carbon stored. Cleaner air means healthier people. These aren't abstract ideals, but measurable outcomes. Earth's habitability resembles a negotiation among biology, chemistry, and physics. Our species entered that negotiation late, but with outsized influence. We've altered the atmosphere, oceans, and land at unprecedented speed. But that influence can also be turned toward protection and repair. When you breathe in now, you're taking part in a cycle billions of years in the making. Oxygen produced by plants, carbon recycled by soil and sea, all entering your lungs. Every choice, in energy, food, travel, and policy, feeds back into that cycle. It's both humbling and empowering. Looking outward at the night sky, space may seem vast and full of alternatives. But for now, Earth is the only place we know that sustains life in such abundance. Its systems are intricate, but not indestructible. Recognizing their limits is not surrender, but awareness. It clarifies where to act and why it matters. This brings us back to the central question of our journey. Not just whether Earth will remain habitable, but which parts will, for how long, and under what conditions. How we answer depends on choices being made now, in governments, companies, communities, and homes. The stakes are high, but the tools exist. The future is not fixed. Within the narrow margins of physics and biology lies a wide field of human action. A planet of 9 billion people can live within planetary boundaries if systems are redesigned. Energy can be clean. Cities can be cooler and greener. Food can be grown regeneratively. Biodiversity can rebound. Each step bends the curve. Understanding this transforms the question from doom to direction. Instead of, will Earth become uninhabitable? We ask, how do we keep it livable? And, what do we restore so it thrives? It's an invitation to participate rather than spectate. As this journey draws toward its final themes, remember that Earth's balance is not just a backdrop, but a relationship. We're woven into it with every breath, bite, and beam of electricity. That relationship can be strained or strengthened. The future depends on which we choose. As we move further along this journey, the picture that emerges is not one of a single catastrophe, but of intertwined pressures and opportunities. Climate, biodiversity, oceans, soil, and technology are linked in loops that can either spiral downward or stabilize upward, depending on our actions. Understanding these linkages helps us navigate the future more wisely. One key element is time. Climate change unfolds over decades, but decisions made now echo for centuries. Carbon dioxide lingers in the atmosphere for hundreds of years. Ice sheets respond slowly, but once set in motion, can continue melting long after emissions stop. Ecosystems take years to recover, but can collapse in months under stress. This asymmetry, slow healing, fast damage, is why early action matters so much. Another element is thresholds. Systems can absorb shocks up to a point, but then shift into new states. The Amazon can turn to savanna. Coral reefs can collapse. Permafrost can thaw and release methane. These tipping points are not distant hypotheticals. Some may be near or already underway. Yet knowing about them also gives leverage. Avoid crossing them, and recovery remains possible. Adaptation, mitigation, and restoration reinforce each other. Renewable energy cuts emissions. Regenerative agriculture stores carbon and improves soil. Biodiversity protection keeps systems resilient. Urban redesign reduces heat and storm impacts. Together, these measures create co-benefits: cleaner air, better health, stronger communities that make change more attractive. Communication matters too. People act on stories and shared visions, not just data. Narratives of possibility counter despair and motivate engagement. Highlighting successful projects, cities cooled with trees, wetlands restored, emissions reduced, shows that action works. Each positive feedback loop we create in society mirrors the positive loops we seek in nature. Economic systems can evolve. Subsidies once favoring fossil fuels can support clean energy and conservation. Investments can shift from short-term extraction to long-term resilience. Businesses can measure success not only in profit, but in impact on ecosystems and communities. These shifts are beginning, but need acceleration. Education and equity underpin all of it. People with knowledge, agency, and resources adapt better and demand more responsible policies. Addressing inequality between nations, regions, and social groups is not only moral, but practical. A stable climate future depends on widespread capacity to adapt and participate. We also need humility. Despite satellites, supercomputers, and centuries of science, Earth remains complex beyond full prediction. Surprises, both positive and negative, will emerge. Building flexibility into systems, diversifying food sources, preserving seed banks, and maintaining emergency capacity are ways to hedge against uncertainty. At the same time, hope is grounded in evidence. Renewable energy scaling faster than expected. Public awareness rising. Conservation reversing some declines. International cooperation slowly strengthening. Each sign, though small, indicates potential momentum. The future is not predetermined. It's a moving average of choices. Our species evolved within Earth's narrow climate band. We adapted to its rhythms, then altered them. Now we stand at a hinge point, where our intelligence, once a survival tool, must become a stewardship tool. The planet's story and our own have merged. Understanding that story, from cosmic accidents to microbial revolutions, from ancient forests to modern cities, shows how rare and precious our context is. Even if no one alive today sees the full outcome of these choices, every act leaves a legacy in carbon levels, forest cover, species survival, and human institutions. Those legacies accumulate into the conditions future generations inherit. Seeing climate as legacy reframes sacrifice as investment. At its heart, the question, will Earth remain habitable, becomes, will we choose to keep it that way? It's not only physics but values, what we prioritize, protect, and imagine possible. And imagination matters. A future of clean air, resilient cities, restored ecosystems, and thriving cultures is not utopia, but a plausible outcome if action aligns with knowledge. This chapter of our journey through time is about recognizing that the systems sustaining us are living, dynamic, and responsive. They can be nurtured as well as exploited. The path forward is difficult but visible. The map is written in science, history, and lived experience. The compass is our collective will. As the 21st century advances, we're writing a chapter of Earth's history that future beings, whether humans or something else, will study as a turning point. The pressures we face are not just environmental, but social, economic, and ethical. They ask what kind of civilization we want to be and how we define progress. Energy transitions are already reshaping geopolitics. Countries investing in renewables and storage gain independence from fossil fuel imports. Regions rich in sunlight and wind may become power exporters. Lithium, cobalt, and rare earths create new supply chains and alliances. Infrastructure built for oil and gas must adapt or be retired. These shifts mirror past transitions, from wood to coal, coal to oil, but faster and with planetary stakes. Cities where most people now live sit at the front lines of climate impact and innovation. Urban heat islands magnify warming. Paved surfaces worsen flooding. But cities can also be laboratories for change. Green roofs, permeable pavements, mass transit, bike lanes, and microgrids reduce emissions and improve resilience. Architecture inspired by local climates, shade, ventilation, reflective materials, cuts energy use and keeps people safer during heat waves. Urban trees cool air, filter pollutants, and improve mental health. Public health ties directly to climate. Warmer temperatures expand the range of mosquitoes and other disease vectors. Heat stress strains hearts and lungs. Pollution exacerbates asthma and other conditions. Disasters disrupt medical supply chains and hospitals. But cleaner energy improves air quality. Active transport like walking and cycling improves health while cutting emissions. Food systems emphasizing plant-based diets reduce chronic disease risks and lighten agriculture's footprint. Security analysts now list climate change as a threat multiplier. Droughts, floods, and storms can destabilize regions already stressed by conflict or weak governance. Migration pressures grow as areas become less livable. Water scarcity triggers disputes over rivers and aquifers. Yet cooperation also emerges, sharing technology, managing watersheds jointly, coordinating disaster response. Whether climate drives conflict or cooperation depends on choices made before crises erupt. Culture and spirituality influence how people respond. Many traditions hold Earth as sacred or emphasize stewardship. Art, literature, and storytelling shape values and mobilize action. Youth movements demand intergenerational justice. Indigenous philosophies frame humans as part of a living web rather than owners of it. These perspectives offer ethical grounding beyond economics or policy. Meanwhile, research into Earth systems continues to deepen. Paleoclimatology, ice cores, tree rings, sediment layers, shows how past climates shifted and how fast. Modeling improves with supercomputers and data. Social sciences explore behavior change, risk perception, and governance. No single field can address the challenge alone. Interdisciplinary collaboration mirrors the interconnectedness of the systems themselves. On the horizon, new technologies blur the line between mitigation and manipulation. Geoengineering proposals, reflecting sunlight with aerosols, brightening clouds, fertilizing oceans, spark fierce debate. Supporters argue these might buy time if warming exceeds targets. Critics warn of unknown side effects, governance gaps, and moral hazard. Even if never deployed, their consideration highlights desperation and the scale of our predicament. Yet despite these tensions, there is a quiet revolution of local actions. Communities restore riverbanks, retrofit homes, plant urban orchards, and install solar panels. Farmers experiment with cover crops and agroforestry. Fishers establish no-take zones to rebuild stocks. Teachers bring climate literacy into classrooms. These scattered efforts form a global tapestry of adaptation and care. Each fraction of a degree avoided, each hectare restored, each species saved, multiplies resilience. The narrative shifts from inevitable decline to ongoing stewardship. This does not erase risk, but reframes it as a shared project. The science gives outlines. People fill them in with practice, policy, and persistence. As we near the end of this journey, we see that Earth's story is still being written. A blend of deep time and immediate action, cosmic luck, and human choice. The question, will Earth remain habitable, no longer sounds like a distant worry, but an everyday guide to decision-making. The patterns of history show that crises can accelerate transformation. When circumstances force adaptation, societies innovate. The Black Death reshaped Europe's labor systems. The Dust Bowl reformed U.S. soil policy. Oil shocks spurred energy efficiency. Climate change is slower but broader. It touches every sector, every region. Its scope makes coordinated action harder, but also more necessary. Transitioning to a low-carbon world will not be uniform. Some regions may leapfrog straight to clean energy, as many did with mobile phones, skipping landlines. Others may cling to legacy systems, longer due to sunk costs or political resistance. Financial systems and international institutions will play roles in financing and guiding this shift. The success of global cooperation in phasing out ozone-depleting substances under the Montreal Protocol shows it's possible to align incentives when the stakes are clear. Behavioral and cultural shifts can be as powerful as technological ones. Norms about car ownership, diet, waste, and consumption shape emissions. Campaigns, education, and incentives can change habits quickly. During crises, wars, pandemics, behaviors shifted almost overnight. With supportive infrastructure, low-carbon lifestyles can be easier and more attractive than high-carbon ones. Future generations will inherit not only environmental conditions, but also narratives about how we responded. Did we delay until forced? Did we act proactively? Did we treat climate as a burden or an opportunity to build something better? These stories influence identity and politics for decades. Seeing climate response as nation-building and community-building rather than sacrifice may motivate faster change. Science fiction often imagines worlds where humans leave Earth, terraform new planets, or live in space habitats. These stories inspire curiosity, but also highlight the uniqueness of Earth's free, breathable air, vast oceans, and complex ecosystems. Terraforming Mars would require centuries and unimaginable resources to approach even a fraction of Earth's comfort. This perspective reframes sustainability, not as restriction, but as preserving an irreplaceable miracle. The long view matters. Even if warming stabilizes, sea levels will rise for centuries due to thermal expansion and ice melt already underway. Ecosystems will shift, and adaptation will continue. The goal is not to freeze the world in one state, but to ensure transitions remain within humanly manageable bounds. Recognizing inevitability alongside agency prevents both fatalism and denial. Our tools for monitoring Earth, satellites, ground sensors, citizen science, give unprecedented visibility. We can track deforestation in real time, map coral bleaching, measure atmospheric gases, and forecast storms days ahead. This visibility can drive accountability, but only if paired with political will and public engagement. Data alone cannot compel action. It must be woven into stories, decisions, and systems of reward and penalty. Ethics extend beyond humans. Our choices affect countless species, many unseen, each with intrinsic value and roles in ecosystems. Some argue for granting legal rights to rivers, forests, or species, recognizing them as stakeholders. This shift from dominion to stewardship reflects an evolving understanding of our place in the biosphere. Ultimately, sustaining Earth's habitability is less about heroics than about countless ordinary decisions. Infrastructure budgets, zoning laws, product designs, daily habits that cumulatively set the course. The quieter, slower choices often matter more than dramatic gestures. The habitability question also returns us to deeper themes: mortality, interdependence, and meaning. Just as individuals plan for their descendants, civilizations can plan for future generations. This long-term view is rare in politics, but natural in ecosystems, where cycles span millennia. Aligning our institutions with those timescales may be the greatest challenge. Looking back at this journey, we've traveled from cosmic beginnings to soil microbes, from ice cores to satellites, from ancient extinctions to modern cities. We've seen how fragile and strong Earth can be. We've examined risks, but also solutions, limits, but also leverage points. The story is still unfolding. The future of habitability lies in cooperation across scales, local, national, and global, because Earth's systems are interconnected beyond any single border. Air moves freely, oceans connect continents, migratory species cross boundaries. No nation can fully insulate itself from climate impacts. This reality shifts security from competition to shared stewardship. At the local level, communities know their terrain best. They can identify vulnerable infrastructure, sacred places, and key ecosystems. Citizen science can track air quality, water levels, and biodiversity. Local governments can design green spaces, protect floodplains, and support neighborhood energy projects. Empowered local action gives resilience and also builds trust between people and institutions. National governments can set standards, regulate emissions, fund research, and invest in infrastructure. Taxes and subsidies shape energy markets. Building codes determine efficiency. Disaster response systems prepare for floods, fires, and storms. Education systems teach climate literacy. These levers work best when stable across election cycles, giving businesses and communities confidence to plan long-term. Internationally, frameworks like the Paris Agreement aim to coordinate action. Global funds support adaptation in vulnerable countries. Trade rules can encourage low-carbon goods. Data sharing improves forecasts. Negotiations are slow but essential because the atmosphere is shared. Even small alignments, phasing out certain pollutants, coordinating early warning systems, protecting migratory species, make large differences when scaled globally. Finance underpins all of this. Shifting trillions from fossil fuels and destructive land use to renewable energy, restoration, and resilience projects is both a challenge and an opportunity. Green bonds, climate funds, insurance innovations, and corporate disclosures are growing. Markets alone won't solve climate change, but can accelerate solutions when rules reward long-term stewardship over short-term extraction. Culture, media, and education shape perception. Stories of disaster can motivate but also paralyze. Stories of repair can inspire. Highlighting local heroes, farmers, engineers, students, normalizes climate action as everyday citizenship. Intergenerational dialogue helps. Elders carry memory of past changes. Youth imagine future possibilities. Together, they create a sense of continuity. Ultimately, the question of habitability circles back to values. Do we measure success purely in GDP, or also in ecosystem health, community well-being, and cultural richness? Do we treat Earth as a stockpile or as a living partner? These questions are philosophical, but have practical consequences in what we build, protect, and pass on. Spiritual traditions can provide grounding. Many emphasize humility, gratitude, and interconnectedness. Rituals tied to seasons or harvests echo ecological cycles. Reviving these links can foster respect for limits and cycles beyond human calendars. This isn't nostalgia, but integration, using ancient insights with modern knowledge. Preparing for change also means building resilience into systems not directly related to climate. Public health, education, governance, and conflict resolution all buffer communities against shocks. A society with strong social safety nets, trusted institutions, and equitable participation weathers crises better. As individuals, our power may seem small compared to global systems, yet habits aggregate. Voting, volunteering, choosing sustainable options, and sharing knowledge create cultural shifts. In a connected world, ideas spread rapidly. Social tipping points, when a minority influence becomes majority practice, can flip norms faster than expected. Seen from space, Earth still glows blue and white, swirling clouds over land and sea. From that vantage, no borders are visible, only the thin shell of atmosphere and the vast ocean. Astronauts often describe an overview effect, a sudden sense of unity and fragility. Bringing that perspective down to daily life is part of the challenge and the opportunity of our time. The journey through time we've taken so far shows both the magnitude of the stakes and the range of possibilities. What happens next will be determined not by fate, but by the sum of countless decisions and the stories we tell ourselves about what is possible. Looking ahead, the task is not merely to avoid the worst, but to build the best. A planet more resilient, equitable, and alive than the one we inherited. This means thinking in decades and centuries, not just election cycles or quarterly earnings. It means investing in systems that regenerate rather than deplete, and measuring success by long-term stability rather than short-term extraction. Science provides the baseline. We know how much greenhouse gas is in the atmosphere, how fast ice sheets are melting, how ecosystems respond to disturbance. Models project possible futures under different scenarios. But science alone cannot choose between those futures. Values and politics do. The more people understand the mechanisms, the more informed the decisions can be. Education and public engagement act as force multipliers. When communities grasp the stakes, they innovate solutions that fit local needs. Youth-led movements have already pushed climate to the forefront of global politics. Universities, museums, and media can translate complex data into stories and tools for action. In business, a new generation of entrepreneurs designs with circularity, low carbon, and resilience from the start. Products are built to last, be repaired, or be recycled. Supply chains become transparent. Investors demand environmental and social performance alongside financial returns. Regulation can reinforce this shift, preventing greenwashing and rewarding genuine impact. Urban planning and architecture offer vivid opportunities. Cities can be designed as carbon sinks with green corridors, rooftop gardens, permeable streets, and mass transit. Buildings can produce more energy than they use, collect rainwater, and support biodiversity. Such designs reduce costs over time, improve health, and create beauty that connects people to their environment. In rural areas, agroecology, permaculture, and indigenous land stewardship provide models of low-impact, high-resilience food systems. Seed diversity and soil health become insurance against shocks. Water harvesting, windbreaks, and mixed cropping mimic natural systems, reducing vulnerability to pests and climate extremes. At the planetary level, protecting large intact ecosystems like the Amazon, Congo Basin, boreal forests, and high seas delivers multiple benefits: carbon storage, climate regulation, biodiversity, and cultural survival. These areas act as planetary safety nets. International cooperation, funding, and enforcement are needed to keep them intact. Human health stands to benefit immensely from climate action. Cleaner air means fewer respiratory illnesses. Active transport reduces obesity and heart disease. Green spaces improve mental health and social cohesion. Shifting diets lowers cancer risk and agricultural pollution. In this way, climate policy doubles as public health policy. Technology will continue to evolve. Perhaps fusion power, advanced storage, new materials, or unforeseen breakthroughs. But no technology can replace functioning ecosystems or the web of relationships that make Earth unique. Recognizing natural systems as infrastructure, wetlands as storm barriers, forests as carbon banks, soil as water filters, reframes conservation as investment. As more people see these connections, cultural norms shift. Plastic bans spread. Plant-based meals appear in schools. Companies advertise carbon footprints. Voters demand action. Incremental changes accumulate until the baseline expectation changes. This social tipping dynamic can be as powerful as any innovation. All of this points toward a future where Earth remains habitable, not by default, but by design. The design of policies, technologies, economies, and cultures aligned with the realities of a finite living planet. Such a future is not guaranteed, but it is possible. In closing this chapter, we stand in a moment of overlapping crises and emerging solutions. Climate change is the backdrop, but also the catalyst for a new era of planetary awareness. Whether that awareness leads to division or solidarity depends on the stories we tell and the choices we make. As the narrative of habitability unfolds, it becomes clear that the question is not only environmental, but civilizational. How we organize our economies, our governance, and our sense of belonging on a single planet. In this sense, climate change acts as a mirror, showing both our strengths and our weaknesses. Resilience is built from diversity, in ecosystems and in societies. Communities with varied energy sources, robust public services, and inclusive decision-making rebound faster from shocks. Monocultures, whether single crops, single industries, or single ideas, tend to fail catastrophically. Encouraging pluralism, innovation, and participation across all levels strengthens collective security. Democracy, transparency, and rule of law support long-term stewardship. When citizens can hold leaders accountable, policies reflect broader interests rather than narrow ones. Corruption undermines environmental protection, while strong institutions can maintain protections across political cycles. This isn't automatic, but must be cultivated. Cultural heritage also plays a role. Traditional knowledge of seasons, water, and biodiversity can complement scientific data. Oral histories capture past floods, droughts, and migrations. Indigenous stewardship demonstrates ways to live within ecosystems rather than above them. Integrating these perspectives enriches adaptation and reduces blind spots. Migration will likely grow as parts of the world become harder to inhabit. Planning for migration, building receiving infrastructure, protecting rights, and easing transitions can prevent humanitarian crises. Viewing migrants not as burdens, but as contributors, can strengthen societies. Historically, migration has often brought innovation, labor, and cultural exchange. Finance mechanisms can buffer shocks. Insurance spreads risk, while climate funds support rebuilding. Microloans and community banks help households adapt. International debt relief tied to conservation, so-called debt-for-nature swaps, can free resources for restoration. Creative approaches like these can align financial incentives with environmental health. Art and narrative remain powerful. Murals on city walls, documentaries, and novels translate statistics into emotion. They help people imagine futures worth striving for and mourn what's lost. Rituals, memorials, and public spaces can honor landscapes and species, creating a shared sense of responsibility. Technology and governance must also anticipate unknown risks. Artificial intelligence, biotechnology, and geoengineering may reshape the future as profoundly as fossil fuels reshaped the past. Building ethical frameworks before deployment reduces harm. Public dialogue and global norms can guide these tools towards stewardship rather than exploitation. International law may evolve to recognize ecocide, severe environmental destruction, alongside genocide and war crimes. Such a step would mark a cultural turning point, acknowledging harm to ecosystems as harm to humanity itself. Meanwhile, corporations face growing legal and reputational risks if they ignore climate responsibilities. Amid these transformations, everyday life may look different, but not necessarily worse. Cities with more trees and less noise, food with fewer chemicals and more diversity, energy bills lower thanks to efficiency, cleaner rivers supporting fish once gone. These are tangible co-benefits of climate action, not abstractions. Children growing up in such environments may see stewardship as normal, not radical. Schools could teach climate literacy as naturally as math or reading. Civic participation in local restoration projects could become a rite of passage. Cultural expectations can shift quickly, redefining what it means to be a good citizen, a successful business, or a responsible leader. In this vision, habitability becomes a shared craft, like tending a vast garden whose health depends on millions of hands. Failures still occur, storms still strike, but the system as a whole absorbs shocks and recovers. Life continues not as a precarious exception, but as a resilient norm. The underlying message of this journey is that Earth is not a passive stage, but a co-actor. Our relationship with it can be extractive or reciprocal. The more reciprocal it becomes, the more stable our own societies will be. Looking still further ahead, the choices made in the next few decades will echo across geological timescales. Carbon released today will influence climate centuries from now. Species saved or lost will shape ecosystems for millennia. Infrastructure built now, roads, dams, cities, will channel water, migration, and energy use far into the future. Seeing our actions through this lens of deep time shifts priorities from short-term gain to long-term stability. Earth's geological record shows abrupt climate shifts, punctuating long periods of stability. Ice ages ended suddenly, ocean currents flipped, and species vanished rapidly compared to the preceding eras. These episodes remind us that planetary systems can move quickly once thresholds are crossed. But the record also shows resilience. After each upheaval, life diversified again. This duality, vulnerability and recovery, defines our opportunity. In practice, sustaining habitability means building buffers, wetlands to absorb floods, seed banks to preserve diversity, redundant grids to maintain power, social safety nets to cushion disruption. These buffers buy time for adaptation and recovery. Without them, small shocks escalate into crises. With them, even major shocks can be absorbed. A key principle emerging from resilient science is modularity. Systems with many semi-independent parts fail less catastrophically than tightly coupled, uniform systems. Diverse crops reduce famine risk. Decentralized power grids prevent blackouts. Polycentric governance allows experimentation and local tailoring. This principle echoes across nature, from coral reefs to forests, and offers a blueprint for human systems. Another principle is feedback awareness. Monitoring indicators, carbon levels, soil health, species counts, ice thickness, allows early response before thresholds are crossed. Just as a thermostat keeps a house comfortable by sensing and adjusting, societies can stabilize planetary systems by measuring and acting quickly. This demands transparency, trust in data, and institutions capable of rapid change. Culturally, adopting a long view requires shifting myths of endless growth to myths of balance, regeneration, and maturity. Many ancient cultures celebrated cycles: planting and harvest, flood and retreat, birth and death. Modern narratives often focus on linear progress and expansion. Reintegrating cyclical thinking could help societies plan beyond single lifetimes. Economically, valuing natural capital, the services ecosystems provide, internalizes costs now borne by the public or future generations. This might mean paying for carbon storage in soils, pollination by insects, or flood control by wetlands. These mechanisms align financial incentives with ecological health, turning preservation into investment rather than charity. Intergenerational governance experiments are emerging. Some nations appoint future generations commissioners to review policies for long-term impacts. Youth councils advise parliaments. Constitutional amendments protect environmental rights. Such steps give voice to those not yet born, but deeply affected. This time stewardship can extend to education. Teaching children about deep time, planetary boundaries, and civic responsibility equips them to make better decisions later. Art, ritual, and public space can anchor these concepts emotionally, as well as intellectually. Despite the magnitude of change needed, humans excel at cooperation when stakes are clear. The eradication of smallpox, the Montreal Protocol, and the global scientific collaboration during pandemics show our capacity to act collectively. Climate change is larger, but not fundamentally different, a shared threat solvable by shared effort. The outcome of this collective experiment will define the Anthropocene, the epoch of human influence. Whether it's remembered as an age of decline or a renaissance of stewardship depends on what happens next. In the most hopeful scenario, our era could be the moment life on Earth became self-aware enough to sustain itself consciously. In that scenario, the thin blue line of atmosphere visible from space becomes not just a boundary, but a symbol of unity. Nations see themselves as stewards rather than owners. Economies reward regeneration. Cities function as ecosystems. Education instills humility and wonder. And future generations inherit a planet still capable of surprise and abundance. Through this entire journey, we've moved from cosmic origins to the thin air we breathe, from ancient forests to modern cities, from the forces that shaped life to the choices that shape its future. Again and again, one truth emerged. Earth's habitability is not a fixed gift, but an ongoing relationship. It endures because billions of systems, biological, chemical, physical, work together in balance. And now, for the first time, one species has enough power to either destabilize or sustain that balance. This realization is both sobering and empowering. It shows that no single action defines the outcome, but every action contributes. From restoring a wetland to shifting an energy grid, from voting for policies to teaching a child about the seasons, each choice helps write the next chapter of Earth's story. The question, will Earth remain habitable, transforms into, how will we keep it habitable? And, what legacy will we leave? These are not distant worries, but immediate guides. Each step toward clean energy, healthy soils, vibrant oceans, and thriving communities is a step toward a future where Earth continues as our home. Not only physically, but culturally, spiritually, and morally. As we close this story, remember that Earth is strong but not invulnerable, vast but finite. It has survived asteroid impacts, ice ages, and mass extinctions. It can survive us too. But whether it remains hospitable to us depends on what we do now. Stewardship is no longer optional, it is survival. Thank you for traveling with us through this reflection. By learning, imagining, and acting, you become part of a global movement to protect and renew the only world we know. The power to shape the future is already in your hands, homes, and communities. We hope you found calm and clarity in this journey. If you did, please consider liking the video and subscribing for more explorations of our past, present, and possible futures. Together, we can turn curiosity into care and knowledge into action. This has been Journey Through Time. Thank you for listening, and may the stories of our planet guide us toward wiser days ahead.